Hey students, welcome back. Dr. G here again. You're going to have a really special treat this week. This week we will hear from Dr. Karin Ardon-Dryer. She's an assistant professor in the Department of Geosciences here at Texas Tech and is an expert on aerosols and how they impact the environment and human health. Let's hear what she has to say. So thank you very much, Dr. Ardon-Dryer, for joining me.
Pleasure.
I'm very honored that you would take the time out of your schedule to talk with us about some of your research and some of the cool stuff that you're doing, frankly.
Thank you.
And so I have a few questions, and I know I sent these questions to you earlier just so you could have some things prepared, but please don't feel restricted to the questions that I ask. If you'd like to extend beyond any of those, I encourage you and welcome you to do so.
All right.
To get us started, I'd like for you to tell us how your research in atmospheric science extends to COVID-19 research.
Sure. All right. So I'm an atmospheric scientist, and I work on aerosol particles. These are small particles that we have in the air. Most of my work is on dust particles, and we're very common to dust storm here in Lubbock. Aerosols are also viruses. Viruses are considered as aerosols, small particles suspended in the air or in liquid, for example, droplets that emit when you're talking. So with knowledge on aerosols, I was hoping to help some of the research that was done here at Tech to understand better some of the stuff that we have question about relating to COVID. For example, identifying if mask will be efficient and which type of mask. We in the lab, we tested different material and different masks. This was a project with a group from engineering department. And we used the techniques that we're using usually in atmospheric sciences world to suspend aerosol particle and to measure them. But here we basically put a barrier, which was the mask. Another project was looking at aerosol that emit through playing the flute. This was a collaborative project with the School of Music with Professor Lisa Gunner. And we had also Professor Michael San Francisco and Professor Emily Bayless from TTU HSC. And we wanted to see how many aerosol will come out from playing the flute, and are there any biological materials? So meaning if you have COVID and you're playing, can you cause other people to get sick because of it? So anything related to aerosols, which COVID unfortunately is one of the things, are things that we can actually do in the atmospheric science.
That's fascinating. I might ask you a little bit more about that here in a few minutes, specifically on those two projects. More generally, when we think of dust storms and clouds and aerosols outdoors, and we know that when we're thinking specifically about COVID, we're talking about social distancing, and even here at Texas Tech, many faculty members took their courses outdoors. What are your thoughts based upon some of your experience, some of your research, whether it's empirical or anecdotal data? What are your thoughts on the behavior of particles or aerosols indoor versus outdoor?
In general, there will be a significant difference between the type of particles you will have indoor and outdoor. Outdoor, you have a lot of natural particles like the dust. Indoor, you would have everything you emit from the house. If you're cooking, if you're smoking inside your house, but sometimes you can have aerosol coming in from the outside into your house through AC or through not very efficient sealing. For example, when COVID hit, I had some of my instrumentation here at home, and I had one of them measuring the outdoor aerosols and one of them were measuring the indoor, and we had a dust storm, and we saw that some of these dust actually penetrate into our home. So we expect in general to see differences in the type and also the concentration of particles that you would have indoor versus outdoor.
That matches and aligns with what we've heard from CDC and other scientists that when they're encouraging social distancing and trying not to sequester yourselves indoors with several folks and that sort of thing.
The biggest issue with the indoor aspect when it comes to COVID is the ventilation. So outside you have wind, you have circulation of the air, which you don't have as efficient indoor. Sometimes you have, HEPA filter or other type of filter that will help you to ventilate. But this virus is so small that you need to have a very, very efficient filter indoor to make sure it will collect these aerosol and not move them to another room, for example.
So that was my next question is, would you consider an HVAC system, basically a virus distribution system within a building or room?
So based on the recent literature that came as this pandemic happened, we have seen a lot of models that do provide some information on the efficient filter that could be used in the heat or ventilation or HVAC system. Some of those filters are considered to be efficient, and these were some of the stuff we actually used as material for the mask because people were using them in mask. And for some of them, we saw that they were effective. They were able to collect most of the particles, but some of them were not good. So it really depends on the material, the fiber sizes that inside these filters, the density of this filter, and maybe if there's also some electric charge that was put on these filters to collect the particles. So there is a difference. Not every filter will be the same.
So, not to, I'm sure that you're still working on publication for these projects, but I'm curious just in terms of public health. We're doing our best to try to get everyone to cover their faces as much as possible with whatever that they have. But obviously not everyone has access to an N95 nor should they, because we try to reserve those for healthcare workers. But what are you seeing? What were you seeing in your data in terms of the efficacy of these different face coverings?
So the big thing that we saw is that definitely not every mask is equivalent. We tested some N95 and we tested also some KN95, which were basically masks from China. These are supposed to be equivalent N95, but NIOSH and CDC did not approve them before the pandemic. They had to go through very specific tests that they do in NIOSH in order to be approved for purchase in the US. And since COVID, a lot of them have been tested and you can actually purchase some of them. We were lucky that all of the ones we used were efficient, but we have seen some KN95 that were really bad, really, really bad, that I would not even use it on myself, obviously, or I would not recommend someone else to use it. And there's also the difference between fabric mask. Obviously, it's very important to wear a mask because you reduce the amount of emission if you have COVID that you will produce. Most of it will get stuck on the mask. You still have some material, some droplets, small one, that might be able to pass through this mask, not if it's an N95, but most of the fabric mask. But still, you're going to reduce the emission. To protect yourself, any cover is good. Any cover is better than no cover. But obviously, if you're working with patient with COVID, our healthcare provider will need to wear the most efficient thing. And what a lot of people don't know is for healthcare provider to use an N95, they need to be to have a test adjustment, meaning that they'll have different masks. And they'll test if these masks are good and in terms of sealing, if they seal their face, making sure they will not be exposed to this particle. Me in person, I went through 5 different masks before I found the one that actually was good for me and protect me. And all of them were good N95 masks.
So literally the same model of mask, but different physical masks, you saw a difference in aerosol exposure.
This was so we tested different type of mask for this project, and we saw some differences. We also saw a difference over time. Some masks started as very efficient, and over time we saw a very big reduction in their efficiency, which is something good if you're wearing your mask for several hours. But one thing that we found, which was one of the most important things, it doesn't matter how good the filter that you're using in the mask. It's important, but that's not the only important thing. The other important thing is how does it actually seal on your face? Because we have different face structure, different size of nose, different shape of chin, and different masks might fit some people, but not others. For example, we use a 3D printing mask that's become very common, but the person that we're doing the fit test on them, it didn't fit him. It was bad. The filter itself on the mask were perfect. But when it came to the mask itself was very bad for that specific person. And in the paper we just submitted, we mentioned these things. So it's not just the material of the mask. It's also how does it fit yourself. That's why for me, I had to go through 5 different masks to find the one that was actually protecting me.
That's fascinating, and it makes it intuitively it makes sense,
Right.
but to actually see it statistically, to see that happen, that's
Right.
alarming, maybe.
Yes.
Because we may think that we're protected, but we're actually not.
Yeah, that's true. But again, with the time frame that we had to protect ourselves against this COVID, because this is not something that happened over many years, and we had time to protect ourselves and find new things. Everything is happening very, fast, because we need to find the best way that we can adapt to the current situation. And the best way now is to have the face cover and just keep the distance.
So, and I'm springing this on you a little bit because this isn't really a question that I had provided you in advance, but it's kind of come up in my mind through our conversation. What were you seeing in terms of particle suspension during your tests? I mean, how, we've heard the 15-minute rule, the 6-foot rule. We've heard all of these rules. Were you seeing consistency in your data with those recommendations?
So we did not examine things related to the distance specifically. I mean, we did try for the flute, but I think our room background was way higher than the emission, so we couldn't really see anything. But we did, so it really depends. For the mask project, we evaluated particles that were roughly in the size range of COVID. They were 250 nanometer size diameter, where COVID is about 150. So not so different than the virus itself. We focus on that. We did not examine other sizes, but we wanted to say, okay, this is the majority of the droplets would be for that size. We know that the larger the particle, the better the protection is. But this was sort of at the gray zone of, I should say, in atmospheric sciences, we call it the greenfield gap. When we talk about collection of aerosols, this is a location where we have the minimum. So the lowest efficiency of collection. And that's why we focus on this size. So for that specific size, we saw the differences between them. We did not examine the distance because for us, it was more important to evaluate what protect you as a person. We know, again, for modeling, this is not something that I am doing, but from the literature, the smaller the particle, the better it is to be suspended in the air for longer distance. When you are talking, even when you are breathing, you emit droplets. Some of them might contain the virus. Their sizes will vary. Some of them might be bigger, especially if you sneeze or cough, they might be bigger. If you're talking, there might be slightly smaller, but you will have some of the bigger one. So the bigger one will fall, but the smaller one could stay suspended in the air for longer.
Do you see that there are more viral particles in larger droplets? For instance, is there multiple virus particles within a droplet, or is it usually one droplet per one particle?
That's $1 million question.
Yeah.
We did not examine it, but it's one of the biggest questions.
Yeah.
For example, why not everyone emit these COVID particles? If you put two people who are sick, they're not, one of them might emit particles, other one will do it a much lower dose. Is this the fact that if someone has symptoms not have we don't know these questions.
Yeah.
So
that reminds me of some of the things you talked about in your project with the flute professor, where you mentioned that you saw differences in emission of particles, different instruments, and so on and so forth. Can you tell us a little bit more about that project?
sure. I think one of the biggest surprise. So I should start by saying that this was a project that came through a very interdisciplinary collaboration, and we wanted to see if playing the flute emit more aerosols. Because here in a school of music, they were playing in rooms, so they need to know if they can actually do that, or do they have to now go outside? How many people can play together? So this was a way for us to sort of bring some of this interdisciplinary knowledge to some of the applicable things for the school of music. So we had about 10 different peoples who were playing the flute, from very experienced to students. And we saw that some of them, we laugh and call them super emitter, because they emit so many particles while playing the flute, and others didn't emit anything, or at the same level of the noise that we had in a room. So the background noise, which is fascinating. We're now hoping to try to understand why, which could help us understand a lot of things, not just for the flute aspect, but also emission of aerosol in general. But we're not the same. Here's one more aspect that show how diverse we are.
I'm curious, did you see any correlation with the experience of the player and the level of emission?
That's where we're getting to. Some of those people who were super emitter were very professional. But we also had some professionals who did not emit as much, and their level of emission was different between them. So we suspect that maybe it is, but maybe there's other aspect.
Very interesting. And this is the scientist in me wondering about methods and processes. Did they play the same piece of music so you controlled for all of those things?
Everything. They had like the exact same procedure. They were sitting in the exact same room, in the exact same distance to the instrument. They were playing the exact same tune over and over and over and over again. At some point, hearing the same thing is boring. But it was very interesting, because even though they were playing the exact same thing, there were differences between the way they were playing.
Interesting.
But yes, no, we had to keep all the variable as constant as much as possible, and just basically change the person.
Yeah. That's fascinating. And so you said you looked across different instruments as well, mostly flute, but you looked at a couple of different instruments?
We just had the chance of having, at the end of this experiment, one of the professor who were playing the trombone, I think, came and just say, I read that we can use this different thing to protect the emission. So he had a socks, he had a mask, and we tried different things, and we just saw a very large emission just from that. But that was just one person for a very short period of time. So, we can turn this into another full experiment, because it's very important to test different peoples.
Absolutely.
Most of the work that are currently, under review, and you can see some of them on different websites, usually examine one or two people.
Mm-hmm.
And we show how important it is to examine different people.
Well, it's critical. we to isolate it to a handful of folks. I think you've demonstrated that that is a bad idea and
Yes.
potentially perilous. So backing up a little bit from COVID specifically, I'm curious about just the air that we breathe, whether indoors or outdoors. Obviously particles of all sizes are suspended in the air that we breathe.
Right.
Um, Tell me a little bit more about your research, on dust particles and on viral and bacterial particles and other aerosols that are just part of our day-to-day life.
Sure. I mean, the things that we do is very diverse. A majority of the work is on dust, but we are looking at the dust from different perspectives. I have a student who are now analyzing, well, actually, we just finished analyzing and we're hoping to submit that in the next few days. Looking at all the dust storm we had here in Lubbock, trying to understand, are they similar? Are they different? We have two different types of dust storms. Some of them are initiating from a large scale meteorological causes, which is known as synoptic. Other are the convective, which are those big walls of dust known as chabub.
Mhm.
So we're trying to understand, are they similar? Are they different? What are the impact on air quality? And we found very interesting things. There are some similarity, but there's also big differences between them. And this can help, for example, the National Weather Service to give an alert so people with different pre-existing condition will know to stay indoor and not exposed to these particles. We also look at the different chemical composition. What's on these particles? What are we breathing? What are the element, mineralogy or chemical that exist on them? Are there any bacteria and fungi on these particles that we breathe? We also have a station located on campus. Actually, now it's not operational. I have it here in my house because we had some issues with the access to campus because you have to make sure the station is operational and we have to visit every day. So we are hopefully now in the spring semester, we'll be able to bring it back. But I've been having it here at home ever since just the beginning of COVID. And we've been monitoring the air quality every minute. And one thing I've seen is we miss so many dust storms that we are not aware that they exist, but they're happening and they're impacting our life. We are breathing these particles, whether we want it or not. So we try to understand that aspect and yes, mainly focus on the dust, but we also have a health component. We have different experiment with a variety of dust storms from around the world that I were able to collect from different good colleagues from the US, from other places. We have a lot of databases from Africa, and we're just trying to understand what are the similarity and differences between these particles and how will they impact our health. We have two different approach that we're looking at. So it's a very biological approach. One of them is examining the particle to cells, lung cells, and look at how many cells will die. And the other one is a single cell approach where we expose these cells to the particles, but we then look at every single cell to see what will happen to it during the exposure, what kind of impact it would have on the cell. So it tells us exactly the time of death of the cell, what type of death. Is it something that can cause inflammation and an asthma attack, or it will not do much? How does it impact the movement of the cell? How does it impact the fact that the cell divide, which is a normal mechanism that we have in our body? So we're trying to understand what's out there, but also what comes in.
Yeah, that's fascinating. Immediately in my mind, I'm trained as a cell biologist, and immediately I think about the mechanical damage of particles onto a cell, as well as osmotic changes.
Yes.
Salts and things of that nature that could be drawing moisture out of the cell that could eventually cause the cell to shrivel or just become non-functional.
Yeah, so these are exactly the kind of stuff that we're looking at. And one of the most interesting thing with the single cell approach is that we can actually see the cell taking the dust particles. They attract for some reason to the particle. We still don't know exactly why, if there's something on it that attract them, or maybe it's a mechanism that the cell willing to sacrifice themselves for the other community. We still don't know those things, but these are observation that we see them taking the cells, the dust. And we also saw in some experiment that as they took more of these particles, they increased their chances of death.
Interesting. So I'm curious, and I apologize. This is so interesting to me. So it was lung epithelial cells that you were looking at?
Yes.
Did you look at immune cells? I'm curious if you looked at things like macrophages and neutrophils, because that's their job is to eat up.
Right. No.
foreign matter.
Yes, exactly. So we have two different type of cells in our lab, and these are just, the type of thing that I worked at Harvard, so I brought them with me. But we're hoping as this technique develop, because it's new, to add more. So we have A549, which are lung epithelial cell, and we also have raw cells. These are mouse macrophage.
Okay.
So we use both. We even mix them together to see the interaction, and we see very interesting things. Both of them are taking the particles. Macrophage obviously is more efficient,
Sure,
but even the A549 that we're using, they're taking the particles.
Fabulous. This is just so interesting. I cannot thank you enough for
Pleasure.
spending some time talking with me about this. I do have one more question about previously what you're talking about air quality, and I believe it's called Aeros. Is that the station that you have?
Yes.
So I know that early on in COVID, when we first started to try to encourage people to stay indoors. And I know that there were countries, specifically in Southeast Asia, that were seeing a significant decrease in their air pollution or an improvement in their air quality.
Right.
Did you see any changes in the air quality or air pollution in the Lubbock or in Texas that would indicate that there were fewer people out on the roads or contributing to air quality?
It's hard to say because overall our air quality here is relatively good.
Okay.
Until we have a dust storm. So it's really hard to say that. And we need to keep in mind that here there were not a complete shutdown when we were not allowed to leave the house. Right. So you had people moving around. Right. In many of these places that you're referring to, in China, in Italy, and there's more and more paper coming out now from European countries, they had a complete shutdown. You were not allowed in the street. So yes, you would see that impact. But most of the impact would come from anthropogenic pollution, which would be related to CO2 or SO2. So mainly gases.
Right.
Could be some of the particles as well. But when we look at when we measure from Aeros, we do not look at the gases. It's hard for me to say, but I only care about the particles.
Sure.
So that's what I'm looking at. I do see some differences. For example, when the station was on campus, we saw a very low particle concentration during the breaks of Christmas because no one was on campus. You didn't have a lot of cars. But I cannot really tell you if it was statistically significant compared to other days, because again, our air quality here is not bad.
Okay.
Until we have a dust storm.
Until we have a dust storm. And when we do, we really have a dust storm, right?
Oh, yeah.
My goodness, this has been a fascinating discussion. I cannot thank you enough. I don't want to take any more of your time, but I so appreciate you taking the time to explain,
my pleasure.
Some of the general aspects of your research, and then some of the specifics about COVID and the College of Music project and the mask project, so on and so forth. This is just fascinating. I cannot thank you enough.
My pleasure.
All right. Well, again, Dr. Karin Ardon-Dryer, thank you so much for your time, and good luck with your research, and please stay healthy.
Thank you. Thank you for having me, and thank you so much.
My pleasure. Thank you.